Okay, we are very happy to introduce today's speaker, Dr. Siyul Lee from KU Leuven. So he will talk about today supersymmetric charge constraint on AdS black holes. Please.
Thank you for the introduction, and thank you all for being here on this Friday afternoon. So as Professor Kim introduced, I will talk about supersymmetric charge constraints on the AdS black holes. To start with, let me remind ourselves why we study AdS black holes. Just black hole is a fantastic object to study in modern physics because it mixes every corner of physics into one simple object, the black hole. If you look at the formula for the Hawking temperature, it has Planck's constant, it has speed of light, Newton's gravitational constant, and Boltzmann constant in one equation. So black hole is really a thermal and quantum object in gravitational theory. Now, in the 1970s, people realized that black holes in classical gravity have macroscopic conserved quantities such as energy and charges. And if you impose that the black hole, for some reason, have temperature and entropy that are proportional to surface gravity and horizon area, just for no reason, then suddenly people found out that this black hole's macroscopic quantities satisfy all laws of thermodynamics from zeros to third. Now, is it a coincidence? Because even if the quantities satisfy certain equation, that doesn't necessarily mean that the black hole is really a thermal object. This formula for the Hawking temperature is on evidence that it's not a coincidence, but the black hole is really a thermal object. By the quantum effect, black holes radiate like a black body precisely with the temperature that was needed to fit the laws of thermodynamics. So that is an evidence that black hole temperature is not just overfeeding the data, but it's telling you that the black hole is really a thermal object. Now, what about the entropy? We would like to now argue that entropy is also a physical, thermal, really thermal property of the black hole. Then the question is, what does it really physically mean for something to have an entropy? And the answer is the microscopic degrees of number of microscopic degrees of freedom. K, Boltzmann constant times log of the number of microscopic degrees of freedom is a physical meaning of the entropy. So we want to find such number of microscopic degrees of freedom from black holes. But unfortunately, in classical general relativity, black holes don't have any internal structure. It's like a gas, except that we know that it consists of molecules. So this is the limitation of the classical gravity. And if there is any successful theory of quantum gravity, what it must do is to identify as many quantum microstates as e to the Bekenstein-Hawking entropy. Now, one reason that the superstring theory is often praised as a plausible model for quantum gravity is exactly this. For some class of flat and supersymmetric black holes made out of grains in superstring theory, this Strominger Papa in their seminal work, they identified the black hole's Bekenstein-Hawking entropy as the number of string in microstates of the superstring theory. But now we have the famous AdS CFT correspondence, and one of its statement is that dual to asymptotically AdS black hole is an ensemble of quantum states in a non-gravitational conformal field theory with one fewer dimension. This opens a new window to study quantum gravity for us from the usual CFTs, because usual CFTs are probably more familiar to us than stringy microstates, for example. And now for better control, I will limit to supersymmetric AdS black holes dual to BPS supersymmetric states in super conformal field theory. There has been a big progress in this direction recently about counting this number of BPS states in the field theory side to match the Bekenstein-Hawking entropy of the AdS black holes. However, although the counting of the BPS stage to account for the Bekenstein-Hawking entropy has been successful, many refined questions still remain. The success was only about counting the states, how many of them are there, but it doesn't really address what are they and what properties do the BPS stage have. One of the refined questions that remain to be answered that I will focus on today is the supersymmetric charge constraint. It has been known for a long time that for AdS black holes to be supersymmetric, it has to satisfy actually two conditions. One, the energy has to be minimal given charges, but also the charges have to satisfy a certain constraint. And the question is, how does that charge constraint arise from the ensemble of quantum stage of BPS stage in the CFT side? So this
question.
Yeah.
When you box the ensemble of quantum states,
yes.
any quantum state in the ensemble corresponds to black hole, or you have some special meaning here for ensemble?
What I mean by ensemble is that to emphasize that the black hole is not dual to just a single state in the Hilbert space, but it's an ensemble of many quantum states in the theory. And here I will constrain to supersymmetric state
Do
BPS.
people nowadays try to identify single operator corresponding to black hole?
Yes, that is true, but it is not that the black hole is a black hole as a gravitational object is dual to that single state, but it is about finding black hole-like states in the field theory that will make up one big black hole as a bulk. Because black hole, as you know from the Bekenstein-Hawking entropy, it consists of many quantum states.
So you're saying we have to find many black hole-like states to match a single black hole in the gravity side. So
Yes.
yeah.
Yes.
So even if you find some like one black hole-like or non-graviton type operator in the CFT side, that's not enough to explain a black hole solution in the gravity.
Yeah, well, it's microcanonical versus canonical. Maybe if you limit the chemical potentials very strictly, maybe you can form an ensemble that's mostly dominated by just one state. It's an ensemble that effectively consists of just one state that could correspond to some very small black hole. However, in generically speaking, a black hole is dual to an ensemble of many quantum states. And this relation is often phrased in terms of z equal to z. Partition function for the gravitational theory is equal to partition function of the CFT, which is a sum over many quantum states in the Hilbert space.
So here ensemble means it's a set of quantum states which have the same thermal quantum number as
Yes,
black hole.
yes. Yeah, and to compare that quantitatively, you might have to compute the partition function with certain chemical potentials.
As for example, in Siyul approach, my approach, then set of Young diagrams fixed, but there exists some different Richardson number correspond to some entropy or different state, some ensemble. I agree.
Right, so this question about the charge constraint will be the first half, well, not first half, but first part of my talk. I will first start with AdS3 black holes, the simplest example. I will introduce how to compute partition function and the index, and how to derive the charge constraint, how the charge constraint is embedded in the representation theory of the field theory side. And then I will introduce a prescription to extend this idea into more higher dimensional, more complicated AdS5 black holes, where I will do a similar thing by introducing partition function, the index, and give you a prescription. I'm calling this a prescription because it's not every step of this prescription is fully justified, but somehow if you follow the doctor's prescription, somehow you will get a very non-trivial answer. And the fact that it's very non-trivial is supported by the fact that this prescription works perfectly well for AdS4, electrically charged AdS4 and AdS7 black holes as well. And then in the second part, a little bit disjoint from the first and also a little bit shorter part, I will revisit some problems in AdS3, namely the stability of AdS3 black holes that is often faced in terms of superradiance. And also this topic will be intimately related to supersymmetric systems that are away from the charge constraint. So this is the outline of my talk, and I will now start with the first part. Let me start by introducing the main character, the black hole in the gravitational side and its supersymmetric limit. The black hole solution that we have in mind lives in AdS3 times S3 spacetime. And from the isometry of this spacetime, we can read off that there are well-defined conserved quantities from SO2,2 from AdS3 side, we have energy and angular momentum. And from the S3 side, we have two left and right are charges. These four quantities are not completely independent from each other, but all known black hole solutions satisfy this inequality, which can be drawn in this two-dimensional E minus J versus Q plane as the blue quadratic line. And the all black hole lives on or above this blue curved line, and the ones that live on the blue line are extremal black holes, which have vanishing Hawking temperature.
What is K?
For K is I'm talking about the gravitational side, so it's a little bit of misnomer, but KL will be dual to the U1R symmetry charge level of the U1R symmetry in the CFT side. And if KL and KR are equal to each other, they will be, so when there's no gravitational anomaly, this K will be related to the three-dimensional gravitational constant by Brown-Henner relation.
So K is another I charge,
K is the central charge in the CFT side.
but in gravity.
In gravity side, it should be understood as the gravitational constant. Under some relation, Brown-Henner relation. Inverse gravitational constant.
Gravitational constant is central charge.
So that is genetic in any dimension, or I guess.
This is for AdS3 black holes.
Right, but the fact that there's some central charge of the CFT is corresponding to the gravitational constant. That relation is very genetic.
That relation, the relation between the central charge of the field theory and gravitational constant in the holographic theory, there are different relations in every dimension, but there are generically a relation that you can translate into each other.
So just for clarification, you just decided to use the CFT product, right?
Well, yes, to match the language, yes. So this is the solution for all known black holes. However, on the other hand, that there's unitarity, which imposes that every black hole's conserved charges have to satisfy this relation as well. And those that saturate this inequality are the supersymmetric black holes. And this inequality can be drawn in the same charge plane as the red straight line. And as you can see, if the black hole is to be supersymmetric, if the AdS3 black hole is to be supersymmetric, because no known solution is there below the blue line, it has to be on the tangent point.
So what is the limit for J goes to 0 and the QL goes to 0? So
J-
it's a full AdS3 solution, just ground state, not a black hole solution.
J goes to 0, Q goes to 0, but finite energy, you mean?
And the 0, I mean, in the case of the energy, there may be some Casimir energy or something.
Yes.
Right. So the inequality, what does it say in that case?
Oh.
The energy is bigger than some negative number.
Yes. So that is exactly the Casimir energy in the AdS3. Yes.
Which is negative in this case.
Yes. So this tells you a simple fact about the supersymmetric AdS3 black holes. For AdS3 black holes to be supersymmetric, there has to be a constraint on the charges, not just any QL, but QL has to be at exactly this point where QL is equal to KL. And then the energy, which is the vertical axis, it has to be minimal given charges. It has to live on the blue or red line. That doesn't matter because that's the same at the BPS point. And provided that these two conditions are met, the entropy of the AdS3 black holes is given by this simple formula in terms of its charges. So these three properties of the supersymmetric AdS3 black holes will be the key for next 30 minutes. Minimal energy, charge constraint, and the entropy.
So usually I thought that the charge constraint is the mass is roughly speaking bigger than some charge. But the constraint on the charge seems not be like that.
Oh yes, maybe then what I call charge constraint is different from what you had in mind. So there is an lower bound on the energy given charges, but what I call charge constraint is not that. It's a relation between charges that excluding the energy.
So that relation does not hold for the vacuum solution to AdS3 case.
For the vacuum solution, the charge constraint, no.
So some of this applies only for black hole solution.
That is correct. That is correct. So these three properties are what we want to see from the field theory side by the AdS-CFT duality. To do that, of course, I will have to introduce what is the CFT dual to this black hole. The dual CFT is obviously two-dimensional CFT with 4,4 supersymmetry. Its superconformal algebra is two copies of n equal 4 small n equal 4 supergirathral algebra, which is SU2/1,1. From the partons of the bosonic partons of the bosonic subalgebra of the supergirathral algebra, we can identify 4 conserved quantities which equate to the counterparts in the gravitational side that I have already used the same alphabet. In the CFT side as well, the all microstage, all quantum stage, by unitarity, they have to satisfy this linear BPS bound, which is the red straight line that you saw before.
The constraint on the charge is Q equal to K.
Yes.
So that seems to mean that the charge is somehow fixed rather than changing.
You mean charge of the quantum state on the field theory?
Is that the charge of the black hole and also the corresponding field theory are charged?
So yes, and this relation refers to the black hole, but we want to see this from the field theory side. So what we want to do is to identify if the BPS stage in the field theory side have this relation as well. But they do not. In the field theory side, there exists BPS stage all along the red line. There are BPS stage with QL not equal to KL as long as their energy satisfy this BPS bound. So what I will argue in next 10 minutes is that by forming an ensemble of quantum states in the field theory side, although individual microstates do not satisfy this relation, their ensemble average can satisfy this relation and match the equation in the gravitational side.
I wonder another thing is, so what is the gravity description of this black hole solution? You need a type rotate BT solution.
Yes, exactly. So it's AdS3 times S3. It's a solution in AdS3 times S3. And the AdS3 part of it is BTC black hole. Exactly. And there are R charges, QL and QR, that comes from S3 part.
Is there analytic solution for the charge rotating BT solution?
Yes.
But then we have some problem with that kind of solution. Charge rotating.
Oh, it's in terms of BTC, it's just rotating, and the charge is coming from non-BTC side. It's S3 fiber toward the BTC black hole. So that charge is different from this charge. It's not a charged BTC black hole, but it's just rotating BTC black hole.
And what is the origin of the charge from the work side?
From the bulk side, it comes from the S3 S3 part.
That should be realized what kind of gauge field from
Yes.
AdS3 part.
Yes,
And that should be interacted with BTC plane.
that is correct. And
That's what the thinking is that we should consider charged rotating.
sorry, can you specify what kind of problem does a charge rotating BTC black holes have?
Usually instruction not for good behavior. Very
But I think the QL and QR are associated with the carton of SO4, right?
Yes.
So you mean that gauge field is not the gauge field in Einstein-Maxwell, three-dimensional Einstein-Maxwell, right? It's not like that.
Well, you can dimensionally reduce S3 and write them as the gauge field in AdS3, yes.
What I mean is this solution is not just like black hole solution constructed in three-dimensional Einstein-Maxwell field, is it? Because then it cannot be charged over. I mean,
Yeah, the origin of this black hole solution comes from the Svetich-Yum 5D rotating black hole solution, and then interpreting it as 6D black string solution, and then going to some decoupling limit. So it's not obviously like a solution of three-dimensional supergravity. It's derived in some.
Either NSNF or RF flux supported AdS3 times S3 backgrounds, and is it relevant?
It should be relevant, but I'm sorry that I'm not very familiar with that construction, so I cannot answer your question.
I guess the spherical solution to the AdS5 solution could be probably uplifted with that. So maybe
Yes.
this one should be also be available in theory. Appropriate.
Yes, I believe it can be uplifted to 10D. I'm sorry, but I'm not expert in that direction, so. Right, so accepting there are certain black holes with these properties, we can now try to address these properties from the field theory side, from the ensemble of BPS states. And first, I will have to address the minimal energy property of the black hole. So as I have argued, dual to supersymmetric black holes, well, dual to any black hole in AdS3 is an ensemble of quantum states in the field theory side. And supersymmetric BPS black hole lives at this point that's on the red straight line. And on the field theory side, there's no states below the red straight line. So what that means is that if some ensemble of quantum states in the field theory is dual to this point, the supersymmetric AdS black holes, it must consist only of quantum states living on the red line. Because there's nothing below the red line. If anything above the red line is mixed into ensemble, the ensemble as a whole can never come back to the red line. So that's an argument that that dual to the supersymmetric black hole is an ensemble of BPS states that lives on the red line. And that addresses the minimal energy condition that the macroscopic average of an ensemble, the macroscopic charges of the ensemble will have to live on the red line as well. But now there are two more questions to be addressed, the charge constraint and the entropy. And to do that, we need a tool to describe an ensemble without any loss of information. Obviously, that tool is called partition function. Partition function is an object that can describe an ensemble without any loss of information by putting in corresponding number of chemical potentials, here mu, omega left and right, as there are charges, J and Q left and right. By summing over all the microstates, all the BPS microstates in the ensemble with this statistical weight given by the chemical potentials, you can define a partition function and it contains all information about the ensemble. There is one problem with this partition function, that it is not robust. So for example, as you change the coupling constant of the theory, the BPS spectrum of the BPS state can change. And as a result, the partition function can change as a function of coupling constant. For example, a BPS state that lives on this point on the charge plane may get anomalous dimension under the variation of coupling constant and lift to being non-BPS. But this kind of lifting only occurs in pairs because, which means that these two states whose charges differ by this amount of this amount have to be lifted simultaneously. Otherwise, if only this state is lifted alone, this state alone cannot form a representation of the superconformal algebra because Q, the supercharge acting on this state, will bring this into this, and then you need this state in the same representation as well. However, now comes the fun part. If you tune the statistical weight, the chemical potential, carefully such that these two states always contribute the opposite, the same in magnitude, but opposite in sign contribution to the partition function, then the net contribution from these two states will vanish. And as a result, the partition function will be independent of the coupling. And this kind of partition function is what we call index, also known in 2 dimension, specifically as elliptic genus. Index is a particular unrefined case of partition function where you impose a certain relation between the chemical potentials. So I have introduced partition function and the index, which is a particular unrefined case of a partition function. Whereas the partition function, as I emphasized, contains all information without any loss of information about the ensemble of states. Index does not in 2 ways. First, index inevitably depends on one fewer arguments because we have imposed one relation. And as a result, it does not distinguish along the red straight line that I'm calling the line of Q action, because acting of the supercharged Q brings this state along the line, along the red straight line. And second, because of this relation between the chemical potentials, the index allows negative statistical weights for some states. And as a result, cancellations between contributions from different states may occur in index, unlike in partition function. Now, this point 1 might not be a problem in counting the BPS states. We don't have to distinguish the states to count the total number of states. But point 2 might be a big problem in counting the states. If 2 states cancel each other, we are obviously not counting both of them. So that will give you a wrong number of states. However, it was found out recently that by tuning the chemical potentials carefully with some complex values to realize this cancellation, despite this cancellation, the index counts the number of microstates faithfully. Let me demonstrate this fact in a very, very simple AdS3 example, which was first done on higher dimensions. So this is the partition function that can be derived from the CFT2 side, that is dual to the AdS3 black holes, where the 3 chemical potentials have a complex relations between each other. The idea of entropy extremization principle to obtain the entropy from the partition function is to simply treat the partition function, the index, as just one refined case of partition function. So you can impose the usual Legendre transformation to turn from canonical to grand canonical to microcanonical ensemble, and you can get the answer for the entropy, the microscopical degeneracy of the state. But since we have imposed the complex relation between the chemical potentials, the answer is also complex. And it doesn't make any sense that the entropy is complex. So what the entropy extremization principle that is now widely accepted in this field does is to just impose that the entropy is real. So the imaginary part, we impose the imaginary part to vanish, and the remaining part is the entropy. And as a result, this complex equation gives you 2 equations. First of them being the entropy formula for the AdS3 supersymmetric black holes, and the second being the charge constraint.
Are you saying this entropy is the full entropy without that cancellation in the index?
Yes, in the gravitational side, the Bekenstein entropy formula.
But this I don't understand this. complex index, complexified index, but index is basically written index minus one to the other.
Yes, it has cancellations between each
Yeah,
other.
but now it's a fake on the cancellation.
Yeah, that was the recent success of the AdS black
What is
hole.
the basic reason of mechanism?
So this is to obstruct the cancellation as much as possible by tuning the phase, complex phase of the weights that each stage have. Actually, I have a very nice demonstration of how to obstruct this cancellation in my thesis. So maybe I can show it later.
So you say phase, it's not just the minus one, you somehow deform it or?
Well, the two stage with exactly this amount of charges differing will inevitably have -1 vector, so they will cancel. However, it is not that we are summing over these two stage. We are summing over some different direction in the charge space, and in that case, there are no two states that are directly canceling each other for a given velocity, and then somehow it works. So it may not work in infinite precision, but at least to the leading order, and there were also some calculations in sub-leading orders.
So rather than summing positive and negative number, you sum only positive number, something like that.
We do sum over all states, including those with negative weights. So it is, so that's why I'm saying the precision is not infinite, but that turned out to work. It is possible to minimize the cancellation enough.
And also this index was not computed exactly.
This one?
Yeah, right, and it's computed in the certain limit, no?
Oh, well,
For CFT it's exact.
it comes from the party-like argument. So you might say it's, yeah. So this looks great, and it looks like the end of my talk, but it isn't, because it was calculated from the index, and the index intrinsically does not distinguish along the red straight line diagonal line that you saw before. The index intrinsically doesn't have any information about where the state is along the red line. So if it tells you that the state is that the average location of the state is at some central point, then you cannot trust it. The index does not have information about that. So somehow the answer comes from this principle. However, it is not a justified derivation. So instead, I will consider full information about where the state lives along the red line. And to do that, we need some representation theory. So in any quantum theory, the Hilbert space will organize into representations of its symmetry algebra. In this case, the two copies of 2D small and for superparameter algebra. So focusing on just one copy of them, there are only two different types of representations, long and short, which makes the analysis much simpler. And both long and short representations have a remarkable property that if you look at the degeneracy, the content of the representation into if you look at the content of the representation, you can express all the weights in the representation using these two quantum numbers, E left and Q left. And within all representation, there is a Z2 symmetry between flipping these values of the charges into this one. So this can be visualized as this. So the numbers represent the degeneracy of states in a one typical short 2D n equal 4 representation. And the Z2 flipping that I showed you earlier corresponds to this tilted mirroring around this blue axis in the center, which is QL equal to KL line. So for example, there are 44 states with this value of E left and Q left, and there are same number of states with this value of E left and Q left. And as a result, if you average over these 44 and these 44 states, then the average value of the charge QL will be equal to KL. But of course, that's only provided that's only possible provided that these two states, this 44 and 44 states, are summed with equal statistical weight. And that condition corresponds to this relation between the chemical potentials. So the upshot is that by considering the partition function, which have all the information about the location of the states, rather than the index, we can derive the statistical, we have the statistical information along this location, along the line of direction, and that can give you the correct charge constraint, the supersymmetric charge constraint of the AdS3 black hole if you impose this condition that these two states along this state along the line of direction are weighted equally. So this was the derivation for the AdS3 black holes, and now we motivated by this, we move on to the AdS5 black holes.
Question. So conclusion was average charge is Q equal K. So you're
Yes.
thinking about black holes are due to this ensemble of states, and somehow this charge constraint is due to the properties of average of states.
Yes. Yes. Yeah, because I have been arguing that the black hole is due to ensemble of states, and when you say macroscopic quantum charge of the ensemble, you take the average given the chemical potential of the grand canyon ensemble.
So, naively, can we say that the index, by allowing some complex numbers,
Yes.
then it is more or less equivalent to the partition function?
I don't think so, because whatever you do with the complex velocities, index really does not distinguish between this one-dimensional parameter line of this all this
So
stage.
you just derived the entropy starting from the index, right?
Yes.
Allowing the complex problems.
Yes.
But so if you calculate other thermodynamic quantities like energy or any other thermodynamic quantity, then can you get or there are some thermodynamic quantities which cannot be obtained from index even if you are allowing some complex numbers, but only from you can get from the partition function? I'd like to see you started that the index is really due to the cancellation and
Yes.
etc. They cannot carry over the whole full information compared to the partition function where they take care of every single state, right?
That is right.
So, but somehow then with some complexification, you showed that actually it is possible to reproduce entropy formula. So how about the other thermodynamic quantities? Are there any some thermodynamic quantities that you cannot get, for example,
From the index? I don't have any other thermodynamic quantities other than this charge constraint that is sensitive to this information along this location.
Another easy thing would be the energy.
Do you have a approach on beta? I mean, if you have, statistical physics,
Yes.
if you have partition function, yeah, the beta derivative gives either energy or even
For the energy,
entropy.
for the energy, all the microstates satisfy this unitarity bound. This unitarity bound. So even if you take the macroscopic sum over them, the macroscopic average will also satisfy this equation, which they should. So this formula for the entropy is not sensitive to where along the red line the states are.
No, I mean, starting from your partition function, this complexified index. Yeah. Do you have a notion of beta there, or the inverse temperature?
So beta conjugate to energy.
Okay.
No, because it's a BPS partition function that where you sum over only BPS states. So as you can see, there should be actually minus beta E, but it's not there because E is given as a function of the charges. So it is all absorbed into.
How do you get the entropy without beta? You just take logarithm of it. Or...
Even without beta, In standard grand canonical ensemble, you will have to perform Legendre transformation to beta and chemical potentials. But in this case, since there's this is equivalent to beta going to infinity limit.
Zero.
Zero temperature, so beta going to infinity.
The micro count.
Yes. So the role of beta and other chemical potentials is not intrinsically different. You can do the same Legendre transformation as you will do with beta and get a microcanonical degeneracy. Right, so everyone is very satisfied with AdS3 result. Let me go to now AdS5. For AdS5 black holes, there are similar properties. So AdS5 black holes, there are known solutions by Vitoski real that lives in AdS5 times S5 spacetime, whose isometry give you now 6 instead of 4 conserved quantities, including 1 energy, 2 angular momenta, and 3 other charges. These all satisfy this similar BPS bound, which is schematically drawn on this 2D charge plane as the same red straight line. And it turns out that this left-hand side turns out to be a sum of 2 squares. So this equation actually gives you two constraints. So of AdS5 black hole to be supersymmetric, it also has to satisfy 2 relations, and we have the same summary as we had for AdS3. First, for the black hole to be supersymmetric, there has to be constraint on the charges, except that this time the constraint between the charges is much more linear and non-trivial than just QL equal to KL. And in addition, the energy has to be saturating the BPS bound, the linear bound, which corresponds to the red line. Provided that these 2 conditions are met, the entropy of the black hole is given by this relatively simple formula.
Where do you get that nonlinear equation?
This, on the gravity side, this is really that all known solutions, all known AdS5 times S5 solutions, it is a 4-parameter family of solutions, whereas there are 5 charges. And if you translate that into the charges, they all satisfy this relation. So when writing down solutions, you will actually use other parameters, 4 parameters, and all solutions are written in terms of them.
Here,
but
there are 6 networks.
there are 5 charges.
5.
Yes, Q1 to 3 and J1 2. So if you calculate Q and J in terms of the parameters, since there are only 4 parameters, there will be 1 relation between them, and this is the relation. So these 3 properties, as we did for AdS3, is what we want to address from the field theory side, which is the famous N equal for Yang-Mills theory. So from its superconformal algebra, we can also identify 1 energy, 2 angular momenta, and 3 R charges that match the corresponding quantities in the gravity side. And also in the 4D N equal for Yang-Mills theory, all quantum microstates satisfy this linear BPS bound. And those that saturate this BPS bound will be the supersymmetric states. Using the similar argument that there's nothing below the red line, we can argue that dual to the supersymmetric black hole that lives on the red straight line is an ensemble of BPS states that live on the red straight line, which are the BPS states. Now it remains to address how this ensemble of BPS states address the other 2 properties of the supersymmetric AdS5 black holes. So similarly, we have a very powerful tool called partition function, where we can define the partition function in terms of all 5 fugacities that are dual to all 5 charges. But there is similar problem with the partition function, that the partition function is not coupling independent. And there was just this argument about these 2 states being lifted always simultaneously. So you can define the chemical potentials to count these 2 states with negative opposite weights. Then it will be, the partition function will be independent of the coupling constant. And that's what we call index. Index is a particular unrefined version of the partition function that has this remarkable property of being coupling independent.
So those paired excitation states, is it BPS?
So when they live on the red line, they are BPS. But-
The one excited is.
Yes, once excited, as you change the coupling constant, they might be in anomalous dimension and lift to being non-BPS. However, that lifting always occur in pairs. So if you were counting this two stage with opposite weights, you are actually not counting this two stage anyways. So that doesn't affect the partition function, and that's how the index is coupling independent.
So when you define the index in taking trace,
Yes.
I thought you are taking trace over the BPS stage only.
Yeah. That's what I'm doing, but even if I am not, the same thing works. So even if I was not summing over only BPS stage, these two stage, even if they are here and here or here and here, whether they are BPS or non-BPS, they contribute opposite weights to the partition function if you impose the condition for the index. So in that case, they have no net contribution this way or the other. So it is still coupling independent.
So you are not allowing generic non-BPS states, but those non-BPS states obtained by some anomalous dimension like that, but you are accepting because it is harmless. Doesn't change anything. Like that.
I am actually only counting over the BPS stage, but I was just arguing that even if you don't, this coupling independence of index will work. But for the prescription that is to come, the next slide, you really need to sum over only the BPS state. So it's a BPS partition function.
So from elementary effect, please remind me. I thought the BPS states that's usually fall into some short representation.
Yes.
But you said also you mentioned long representation.
That was for the AdS3 CFT2. Yes.
That's a generic only. I mean that's only for the AdS3. Not in this case.
Yes. That's a good point. That I was not being very consistent with taking only BPS or also taking into account non-BPS. That property that you saw earlier about the representation is a property of both short and long. So yes. So there we didn't really have to sum over only BPS stage, even if we had sum over non-BPS stage as well, since it's a sum over all representations that will have worked but for AdS5 now we really have to restrict to BPS stage.
In your AdS CFT2 example, have you specified your CFT2? What is the coupling constant there?
No, I have not. So it was 2D equal 4,4 superconformal field theory, and I had no other information other than that because all representation in that algebra satisfied that.
Yeah, so CFT2 is given by superconformal, blah, central charge.
Yes.
I don't see any coupling constant.
Yes, you did not, because whatever the coupling constant is, whatever the other CFT data is, it doesn't change that the Hilbert space organized into sum over its representations of the Virasor algebra. So we did not have to specify any other data of the theory.
Okay. Good.
So this is the definition of partition function and the index for the AdS5 theory. There's similar two issues that the index does not distinguish along the red line, and also the cancellation may occur. However, despite the cancellation, by tuning the complex chemical potentials to have complex values, the index can count the microstage faithfully. And this was a major breakthrough in 2018, that starting with this partition function that can be derived from the field theory side, you can just perform our Legendre transformation to get a complex answer for entropy. And then by imposing that the entropy has to be real, we will get two equations, one of them being the entropy and one of them being the charge constraint. However, again, the index does not distinguish between along the red line. So it intrinsically does not have any information about where the state live along the red line. So it should not give you the charge constraint, which is the information about the location of the state. So what can we do with this? Maybe we can compute the partition function, but since the partition function is not coupling independent, and computing the strong coupled partition function in strongly coupled and equal Yang-Mills theory will not be viable. But from the hint from the AdS3 side, we can look at the representation of the dual field theory. So now I will give you a prescription to derive this AdS5 charge constraint. So we start with free theory, where the representation is most faithful to the theory. In free and equal Yang-Mills theory, all BPS states consist of single particle states geniously named into letters, and their multi-particle combinations, the product of them, called words. This is the full list of single particle states in n equal Yang-Mills theory. The letters, there are 3 scalars, 3 Carolinos, 2 gauginos, gauge fields, and any number of derivatives acting on them. So any combination of these states, these fields, acting on biderivatives and taking product of them will be the viable BPS stage in the free and equal Yang-Mills theory. First, we can write down the single particle partition function, or partition function only over the BPS single particle letters. And that can be written in a closed form because there are only a finite number of scalars, Carolinos, gauginos. So this is the contribution from scalars, from Carolinos, gauginos, gauge field, minus the equation of motion. And these 2 vectors in the denominator stands for 2 derivatives. Now, given the single particle partition function, we now have to calculate the multi-particle partition function. And a simple way to do that is to take a simple exponential. It might be the most quantum thing, it might not be the most correct quantum thing to do, but it is what you do with classical ideal guess, for example. It is valid in some statistical case. And this is a prescription.
Is it the partition function or index?
This is a partition function. This is a partition function where the 5 velocities P, Q, X, Y, Z are all independent from each other. So the part of the prescription which is not fully justified is to take exponential of the single particle partition function to calculate the multi-particle partition function. And then from the multi-particle partition function, which is the partition function for the full ensemble, you can compute the macroscopic charges as the ensemble averages from these familiar formulas that you learned from undergrad stat mech. Then finally, as we were motivated from the AdS3 side, we imposed that the states along the line of Q action are now weighted equally. That corresponds to this condition between the velocities XYZ, product of XYZ is equal to P times Q. And by imposing this relation, there comes a relation between the macroscopic charges, which is miraculously the same as the charge constraint for the AdS5 black holes, except that n square over 2 vector that was there for the AdS5 black holes have to be replaced by 1. First, we have not included any gauge degree of freedom in this prescription, so this prescription doesn't have any information about n. And if you ask why, I don't know. And there will be a discussion about this in a few slides. But before that, let me emphasize that the same computation can be done for AdS4 and AdS7 black holes. For AdS4 black holes, there is a similar charge constraint for the black hole to be supersymmetric, which is very even more non-trivial than the AdS5 version because there are now 4 electric charges. But we can derive the same charge constraint from the representation theory by considering the dual CFTs superconformal algebra, which is 3D n equal 8 superconformal algebra. And in 3D n equal 8 algebra, there is a unique free multiplet called free hypermultiplet. By taking a single particle partition function over those over the contents of the n equal 3D n equal 8 free hypermultiplet. You can write down the single particle partition function. And as a prescription tells you, take simple exponential to get the full partition function of the ensemble and calculate the ensemble averages for the macroscopic charges. You get the answer for the charges, and finally impose that the states along the line of true action, along the diagonal red line, are counted with equal statistical weight. Then you recover the same charge constraint for the AdS for black holes. Except again, since we have not taken into account any gauge degrees of freedom, the answer does not contain any n. So this is the relation that you will get by replacing n by 9/2 in the black hole's charge constraint.
This multi-particle partition function, if I think about this expansion of this exponential, it looks like you don't care about whether it's boson or family.
That is correct.
Identical.
It is what you do for classical statistical mechanics, not bosonic or fermionic
Still identical.
quantum statistics.
Divide
No.
by n factorial.
Yes,
So it looks like a bit approximation.
it is an approximation. This is a correct. So if you take into account quantum statistics, you will have to use a plastic exponential. It's 1/1 minus x if it's bosonic, 1 plus x if it's fermionic, but they are to the first order in x, same as e to the x. But this is the approximation in that sense.
So if we consider the partition function in the bar, usually they are divergent. So we
Yes.
have to do some regularize
Right.
and normalize. But in the CFT side, there is no such thing. It's all finite from the beginning.
In this prescription, there's no infinity, there's no subtleties. There are finite, well, not finite number, but a finite number of geometric series for the single particle letters. You can all identify them, and just taking the simple exponential of them doesn't cause any divergence.
And there's some simple reason why in the bulk side, even though it's the starting point is a classical, you have to some regularize and
We do
normalize.
have to.
While in the full quantum CFT, of course, it is a CFT, but even inside of that full quantum level, there is no need for any infinity.
Well, first, this is not full quantum theory. It's a very simple prescription, and this is free field theory. So this is not a full quantum theory. And even though you might ask why there's no divergence in this case, and the answer is I don't know. This is kind of miracle for me that it works.
But this is all discrete sum.
It is. So
There's no continuous integral.
right. So there's no room for infinity to enter in this prescription.
If there are interaction, then it's quite different.
It will be very, very different. This is for free theory.
Then all the infinities will also appear.
With interactions, maybe.
Because in principle, in the week, since this is free theory result, you could do some perspective way.
Yes.
And the copying is not big.
Yes. Yeah, and doing that will be a topic of integrability where you compute the partition function as a function of coupling constant. That will be very hard, which I did not do. And the same story for AdS7 that I cannot skip because the most general AdS7 solution have been found by no one else than Professor Hong here. It also has a very non-trivial charge constraint between its charges, and that can be also derived from the unique free multiplet in the dual 62,0 superprofessional algebra. Writing the single particle partition function, taking a simple exponential, taking the ensemble averages to compute the macroscopic charges, and finally imposing this condition that the stage along the red line are counted equally. Then you recover this relation, which is the charge constraint that you saw on the previous slide, except that n cube has to be related by this O1 factor.
So in the example of AdS5 and AdS4, AdS7,
Yes.
in terms of charges, like R charges or angular momentum, there was some relation, right? Either equality constraint or inequality.
Yes.
Right? So the summation means over within that constraint, right?
Do you mean this constraint?
Oh, yeah, for example.
Yes.
Yeah. So when we take the trace, we have to take the trace with that one, or so there must be also relation between the charges, not the chemical potentials P, Q, X, Y, Z.
So it's the order of doing things that is important. What we do is to take the derivative of log C to calculate the macroscopic charges and then impose the relation between the chemical potentials. So that is different from taking this relation between chemical potentials in the first place, because then you lose all information about this one codimension one line. However, if you take the derivative and evaluate that derivative at certain point that is given by this constraint, it still gives you the full information about all the 5-dimensional charge space. So this is the end of magic, which is not mathematic. And now we have to get back to reality and discuss. So what we have done right is to derive the supersymmetric charge constraint from AdS 4, 5, and 7 black holes from the BPS states in the free theories. And this derivation was based on the partition function instead of the index. So it does contain some information about where the state lives along the red line. However, there are things that we have put under the rug in the prescription. First, as you all pointed out, the constraint has been derived with these factors of some powers of n and some O1 factors equated to 1 for no reason. Also, we have not considered any gauge degrees of freedom. That's why we didn't have any factor of n in our answer. So we can say that we have effectively worked in a U1 gauge theory. Finally, the partition function is obviously not coupling independent, but we have calculated the partition function and everything in the free theory, whereas the black hole should be dual to strongly coupled field theory. So there are 3 limitations. However, a possible resolution to these 3 points might be related to each other. For one thing, we have effectively worked in U1 theory, but if we have worked on in UN, where n is large, gauge theory, then what could have been different? So in the confined phase of the UN gauge theory, where n is large, it is known that all macroscopic quantities, extensive quantities, charges, energies, and entropy, they scale as these powers of n, which is related to inverse Newton's constant in the AdS dictionary. So you can scale all the macroscopic quantities that appeared in the charge constraint by appropriate powers of n, and that will at least recover the powers of n part of these vectors that were different from the 2 results. Also, this fact that we have only considered the free theory has an ability to account for the O1 factor that was in front of this powers of n, because with strong coupling instead of the free theory, maybe a fraction of the BPS state in free theory might lead to non-BPS. However, that fraction should not scale with n. Otherwise, the index also, when counting the number of BPS states, would not be able to give you the correct answer when calculated with small couplings. So although not fully answered, these 2 factors are something that might play with each other to address these factors that was put under the rug. So this is, yeah.
That last sentence, fraction of BPS state lead to non-BPS. Is it related to the fortuitous operator?
I did not have that in mind. No. But it's a related topic, so maybe it's possible to find some relation. So this is the end of my first part. And I think it's reasonable to insist that my talk consists of only 1 part. Does that work?
You have 3 pages left.
Yeah, it's a very short second part.
Just skip.
Well, okay, maybe 5 minutes. So let's get back to this picture that you have been seeing again and again. There is extremality bound where all known black hole solutions live above this extremality bound, on or above, but everything below the red line is forbidden by unitarity. And now here is one of my favorite quotes in physics. So maybe compulsory is a bit too strong, but we know that in physics, usually if something is not forbidden, it's usually there. So this gap between the extremality and unitarity bound is a little bit uncomfortable. Why are these states not forbidden by any principle, including unitarity, but why are there no such solutions? There have been some proposal in this direction recently by Minwalla and friends. Also, Minwalla gave related talks in KITP and Strings this year. Although not all results were published, these talks have decent amount of discussion about this. The answer is that this gap between the two bounds might be filled by some composite systems that is not just a black hole, but a black hole surrounded by some other object. That other object could be gas of gravitons or giant gravitons. So this is really
Hairy black hole.
yes, exactly. So this is related to two aspects of the black hole. First is the stability. Black hole might be unstable, which means that it has to compete with some other composite systems in terms of who are more dominant in the ensemble. And this is related to the supersymmetric configuration away from the charge constraint, because if this is true, that means there might be a composite system that lives on, for example, this point, which is supersymmetric, but it is away from the charge constraint. Now, what I will do is to address this scenario for a very simple AdS3 black holes, where there are very simple charge constraint and only 3 charges. So given any AdS3 black holes that I have introduced in the earlier part of my talk, suppose that the black hole emits a chiral primary with these quantum numbers. That will change the charge of the black hole. They will change the charge of the black hole by some infinitesimal amount, because these will translate into some microscopical units. And as a result, from the first law of thermodynamics, you can compute the change in black hole's entropy. And the change in black hole's entropy in when it emits the chiral primary may be positive if its charge QR, for example, is larger than KR. It will be Q left bigger than K left if it was emitting the anti-chiral primary. And this phenomenon is known as superradiance, where the black hole dumps a positive energy to somewhere else, but its entropy increases, so it's a spontaneous phenomenon. It is also known as energy mining or black hole bomb by Soviet scientists. So drawing on this diagram, this means that if you started from a black hole, a perfectly legitimate black hole at here, it might emit chiral primaries so that its charges, so that its macroscopic charges come to this point. However, this process is spontaneous, and the entropy at this point of the black hole is larger than what it had before.
I have a simple question. I'm sorry.
Yes.
Yeah, it's in your the material, superradiance, black hole entropy increase while the emitting positive energy. So could you explain that more clearly in detail? Why the black hole entropy increase?
Oh yeah.
Yeah. So it's usually the black hole, the area will be decreased when emitting something.
Yes.
Yeah.
That is true. So if you look at the first law of thermodynamics at the top, if there were no charges, J, QL, K, QR, if they were all not there, then TdS equal to dE. And when the black hole emits positive energy, its energy decreases. So dE is negative and ds will also be negative. That's the usual situation. However, if when black hole dumps the energy, but also it dumps some of its angular momentum or charges, then the sum in the right-hand side might be positive, even if dE is negative. So that's how the superradiance come about.
Actually, in this case, the black hole is the extremer. Well,
In this case, I'm not committing to any extremal black holes. In the
yeah.
in the picture on the lower right side, the before and after, the 2 points are all not extremal. Extremality bound is the blue curve.
Okay. Yeah. Thank you.
So the scenario is that the black hole might spontaneously decay, and as a result of this emission of chiral primaries, so we can track what happens to the emitted chiral primary particles. And by calculating the trajectory, classical trajectory of the emitted chiral primary particles in the black hole background, we can see that the emitted particles will escape from the black hole without any turning point, except that when the black hole reaches this after point, their radial velocity will vanish, will converge to zero, meaning that at the final product of this decay, there will be a marginally stable black hole that is living on this point in the center, which is the stability, saturation of the stability condition, surrounded by the particles it has emitted, but they are now having, they all have vanishing radial velocity, so they are rotating in a circular orbit. And this is related to the configurations away from the charge constraint, because the question of the stability is about what is the most entropic configuration given the total charges. It's the competition that makes this all instability business. So the question is who wins the competition within the microcanonical ensemble with given total charges, and who is the most entropic within the microcanonical ensemble. And the answer that this black hole before decays into this after state of the black hole is that this marginally stable black hole surrounded by the chiral primary particles that it has emitted, which makes up for this purple arrow, have larger entropy than this before state where there was only a black hole without any chiral primary particles. And this suggests another scenario where there is no known black hole solution. At this point between the gap, there's no known black hole solution as a solution of black hole, but without any chiral primaries. But this implies that there could be a marginally stable black hole at this point, surrounded by enough number of chiral primaries to bring the total charge of the system from here to here. So at this point, at this values of total charges in the microcanonical ensemble, there could be a composite system of black hole and chiral primaries whose entropy is the maximum among all systems with that total charges. And restricting to this scenario onto this red, no longer red, but diagonal line, this gives you an answer of whether there could be supersymmetric configurations away from the charge constraint, which is exactly this point.
Excuse me, can you look at this, or this, can you say something about this from the other side, looking at, say, the weak gravity conjecture? So that's where, like, the charge to mass ratio of a particle should not be a black hole, essentially. So it should be above the black hole extremality.
I have not thought about that direction, but that could be certainly related. So yeah.
Right. Yeah, that would be interesting.
Yeah, thank you for the comment. So this is really all of part 2, I had to say, and thank you all for listening.
Second question: what is the difference from spray Gauss solution?
It's same, except that it's an AdS3. So Minola, in one of his talk in KITP, he said in AdS3 there's no such scenario.
So he was wrong.
That's our implication.
I have some questions, but maybe I can ask it in the videos.
So, about your final slide,
Mhm.
it seems to me that you have argued that such transition from black holes to other things, complex systems,
Yes.
by using the entropy argument.
Yes.
Do you have a dynamic argument for the transition?
No. No.
It is
So-
very difficult to imagine going beyond the extremality of black holes.
That is absolutely right. Yeah. So this is a very basic argument that this might be kinematically possible, and at least entropically it's favored. But yes, we don't have any specific theory with scalars in the gravity theory, and we don't have any rules for dynamics. So I'm cautious in saying that Minola was wrong, because what he did for AdS5 or AdS5 from, for example, 14 years ago, he really considered a full theory where there is a scalar, where there is a consistent truncation, there is a metric, that there's gravity, and there is a consistent coupling to minimal coupling to a scalar field, and he computed all the perturbation with that scalar. That's how we got the hairy black hole solution. So that's how you incorporate dynamics into this scenario. But that's not what I did. This is a much more basic and simpler elementary argument. So, yeah.
I have an elementary question. I'm not expert in holography, so I'm asking this. So if I specify your gravity, if I realize your AdS 3 gravity within string theory, like type 2A or 2B topography, then is there, what more than one dual CFT2? Did you imply?
Because I said it's dual to ensemble of states.
No, I mean the dual CFT2.
Yes.
Is it unique or not?
If you embed this black hole into 10 dimension.
It looks like you don't, only though you need what you need is miraculized block with
Yes.
central charge. I'm not asking about unique cases. We know AdS 5 is any proposal,
Yeah.
unique, but I'm asking the.
I don't have an answer to that question, sir.
Anyone?
I think, there must be just unique CFT, but based on this argument, if you want to derive some holography, you must specify certain CFT flow to the string theory of your best. So if you specify the string theory around this AdS 3 times T4 or whatever, then the dual CFT, I think it has to be specified. But I think his point is he doesn't need that information.
Yeah, that I understood,
Yeah.
but
I think there must be one CFT.
Or I guess what you consider this the maximum Suji case, isn't it?
This black hole is 1/4 BPS, the AdS 3 black hole.
Right, so so starting from the maximum Suji, then you have a quarter BPS.
Yes.
In the black hole.
Yes.
So in that sense, I guess, then once we are specifying a Suji maximally, then the maximal Suji theory seems to be unique. But once the Suji is not maximal, there seems to be many varieties of the CFT. Isn't it?
candidate, but the question is whether there's only true one dual CFT2.
Like this, what we conclude is starting from the maximum, then consider the black hole which is probably.
I think this AdS 3 times T4 has to be a certain decoupling limit of certain grain setup. And then if you go to the open string regime, the open string viewpoint, the Lorentz dynamics of that grain has to be certain CFT. It has to be specified somehow, but I don't know what that CFT is, but it has to be unique.
Yeah, if then you just do some brain picture, then I think there should be some one theory. Other questions?
I have one naive question.
Sure.
You construct the multi-particle particle function just exponentially
Yes.
taking single particle level function. How about using a plastic exponential and compute down somewhere version?
Obviously, that will not work because exponential worked, and it's different. So what we think is that this coincidence between the two results on two sides is a hint that this might be a very valid approximation under some circumstances that is relevant.